So due to the abundance of public holidays overlapping with our workshop sessions, we will actually cover the second half of EM today. Which is basically we'll spend some time. I think it's actually a good lecture to be doing this because there's lots of revising material in case you guys have sort of put this off over the teaching break, and it's a good refresher. And then we'll dive right in. The comic today is mainly chosen because we will be talking a lot about probabilistic models. And sometimes XKCD can be a little bit romantic and sentimental. So the housekeeping for today is that for those of you who are doing assignment and auditing the class, it's assignment 1 is graded. We'll talk about this at the end. And then assignment 2 will be released by the end of this week. And as the course website declares, it's due in week 11, beginning of week 11. So you will have a little more than 3 weeks to work on it. There will be 3 questions. We will spend some time talking about it once it's released, likely Monday of next week. There is a preliminary final exam slot on 8th of June, which I believe is Tuesday afternoon slot in Canberra, and everybody will be doing this synchronously on Wattle. Again, of course, we will talk about this closer to time and when it's finalized. So this is what we are going to really talk about. So I hope you all remember well how EM algorithm works for both K-means and Gaussian mixture models. And we will start with that. We will actually, the main thing for today are basically 2 alternative views of EM. We'll get to them, very big technical. I think an important conceptual gain or that you will get is connections between Gaussian mixture models and K-means. Basically, they look different, but what exactly is different and how are they connected? And then at the end, these are content outside of the book. I won't hold you responsible for this in the final exam. And they are rather recent developments on the topic of clustering, because the topic clustering is rather old, and I just wanted to give people a taste about what's happening recently and in the last, say, like 2006 is not. It's sort of rather recent after the book was published. So that's that. So here is the entire last lecture in one slide. How do we do K-means and Gaussian mixture models? So what we do is essentially we first initialize a set of cluster centers and component means. Somehow, we haven't really talked about implementation and initialization strategy. But for K-means, for example, we can choose a set of data points. And in the recent development section, we're going to talk about a good way to choose a set of data points versus bad ways to choose a data. So there is basically good and bad way of doing this. And then I claim that we only need to initialize component means in Gaussian mixture models and not necessarily the covariances. Because of 2 things. Remember that we briefly mentioned that Gaussian mixture models is usually initialized with K-means. Or maybe we didn't, I forgot how much we talked about that, but we will see that again. So K-means does not have covariance matrices. This also means that we can essentially evaluate a Gaussian mixture model, pretending there is no covariance matrices, or implicitly speaking, the covariance matrices are all the same. This will become, if it's not yet clearer later on. So the algorithm for both models are separated into two general steps. In the expectation step, in K-means, we have basically looked at these two algorithms vertically in columns. Now we're going to look across rows. In K-means, we essentially, given the data centers, reassign data points to cluster centers. We determine this what's called responsibility variable R of the data point n of the cluster center K, which is like either a data point solely belongs to a cluster or not at all. In Gaussian mixture models in the E step, we compute this, again, a responsibility variable or posterior probability of essentially P of Z, the cluster membership, given X. And because we're Bayesian, we said it's given theta, the variables. It's not called R, it's gamma of Z and K. It's basically the conditional of P of X given Z over normalized by all different, the same X over all different possible components. Right, so this is a number between 0 and 1, right, as we can see. Okay, I'm just gonna make the interval closed right now. There are basically corner cases, right, but usually it's basically a real number between 0 and 1. So we can see some similarities, the notion of responsibility and obvious differences. And then we use these responsibility variables to do the maximization step. In K-means, we simply recompute the cluster means by taking, essentially, we take the average, right, averaging over data points in cluster K to get mu K, right? And then in Gaussian mixture models, we are kind of doing the same, where we're essentially doing a weighted average of the data point K, where the weights are these responsibility variables, and the normalization factor is essentially the sum of these responsibility variables for the cluster over all data points. So as we can see, the 9.24 is again a slightly more general version of K-means. You can even start to imagine that if I, let's say if I'm lazy in one of the E steps, I can plug in the card assignment or the response R and K from K-means, and then I can still do the M step, right? Except in here, 9.27 will become essentially the number of data points in cluster, right? Or in fact, the n sub k is the weighted effective number of data points in that cluster. And then I can still compute the cluster covariance, which will become essentially the covariance matrix of the data assigned to that cluster, and similarly for the pi variable too. It's just a fraction of data points assigned to that cluster. So here is a picture of what we just said, right? So if we take, we mentally draw the responsibility as a matrix, right? So we say there are n rows, that's the number of data points, and then k columns, one for each cluster or mixture component. So basically, the E step fills this matrix with either the hard assignment R sub nk or the soft assignment gamma of Z nk, right? For K-means, we compute this as a hard assignment. For GMM, we compute this as soft assignment. So in what case are they equivalent, right? So we talked about covariance matrices and why we sort of don't need them like in K-means, right? So here is one way to convert the two between each other. So if we assume a Gaussian mixture model and assume isotropic covariance matrices given by a scaled, or basically the identity matrix. Basically, covariance is the same across all dimensions, and the dimensions are uncorrelated, where epsilon is shared by all components. So covariances of all components are also the same, right? So all covariances is a small ball, right, essentially. Then we can compute the data likelihood within each cluster by writing out the Gaussian. We can recompute the responsibility gamma of Z and K by simply doing this. If we take the limit of epsilon going to 0, we essentially recover the hard assignment variable R and K from these responsibility, posterior probabilities gamma of Z and K. Right. So that's nice. So what does this mean? So what does this mean for EM algorithm in general? So this is our first view of like an alternative view of expectation maximization. We're going to spend some time here. It's a little bit, there's a bunch of new notations, but let's just go through it. Right, so as we saw in the last lecture, we had a graphical model representation of the Gaussian or latent variable model. Basically, the clear node Z of n is Z is unobserved, and then the shaded node X is observed, and this particular plate notation, which is rather popular or common in probabilistic graphical models, denotes there is n copies of instantiation of this. In this case, it just denotes there's a data set of size n, right? And each of these Z and X are influenced by parts of the parameter theta. We can be more specific, but here I'm just going to write out theta so that this graphic corresponds to equation 9.29. So the conventional data likelihood, basically probability of data given model parameters, as we have been dealing with in linear regression, classification, and so on and so forth, can be written as follows. So basically, we are going to need to marginalize over the Z. Basically, P, we take the joint probability of P of X and Z, and then sum over Z, marginalize over Z, and take the log, right? As we saw, this is not a very nice quantity to directly compute on because log on sums, we can't just break it apart. And we compute the posterior probability as the responsibility variables. And then what we do is we take expectation of the complete data likelihood of P of X and Z, joint of X and Z, with respect to Z. So this expression 9.30 is the main new thing in this part of the content, right? It's this it's called the curly Q, and it has it's a function of theta, and it's also implicitly a function. So it's also a function of X, the data data points, or x1 through n. It's going to be explicit because we're doing this over a data set. So let's first read it, and then we look at the two thetas. So there's a summation. It's sort of a summing over z. The first part is the conditional probability of z given x and some parameters. So this is pretty familiar, right? It's right here. So it's just the posteriors, responsibility variables as we've been staring at in the last few minutes. And the second part is the joint probability of x and z, given some other theta, and taking the log. So what this is, like for GMMs, it's basically pi k and then the normal of x given mu k and sigma k, right? So this is also pretty simple. What is perhaps not obvious to people new to machine learning at the beginning is if we put this together, what does it mean, right? So this expression is essentially the expectation we're averaging over. Informally, what this is we're averaging over some probability of z, which is upfront here, given x, and some set of parameters on some other function. Let's say some other function of x and z given new parameters. So with this expression, we can now try and make sense of, well, theta old, the set of parameters that we're computing the conditional probability on. We want to be able to sort of have a analytical expression of this conditional expectation. So theta old is the theta that we pretend we know, or it's the current value of theta. And then these theta new, or this theta without superscripts, is one that we, in the process of maximum likelihood or similar optimization, we wish to sort of optimize. So these are variables. Also note that if we take the expectation over a conditional probability, the variable x that is still being conditioned on, so it kind of stays in this whole expression. So what this does, right? What we do to this curly q expression is that we essentially maximize this over the variable theta, and we get a new theta. All right, and because q is it still depends on x, so it's similar to the log likelihood upstairs in spirit. So let's so we just assume that this is a valid procedure right now, and then we'll talk in the second half of this session why this is a valid procedure and why it maximizes likelihood, right? All right. So that's a little bit technical. And just to reiterate this, right, what we just said is, right, we, the entire EM procedure with this new formulation inserted rather than the specific E step and M step. Note that we call this a general EM algorithm because this is this is applicable to a lot more than to basically any latent variable, then GMM and K-means. So we will see an example right after this, and you will see, you get to practice this in assignment 2. Right, so again, we choose some initial setting for initial parameters. We evaluate the conditional, conditional of the latent variable given data and parameters, basically the responsibility variables. And the M step, what we do is we maximize this Q function, which we talked about, which is essentially the conditional expectation of Z of the joint data likelihood or complete data likelihood with respect to the conditional probability of the latent variables. Note that since we've been talking about posteriors and so on, we could also sort of use add the prior probability of the zetas, prior likelihood or log likelihood of the zetas to this Q function for a Bayesian estimate, right? So for now, this EM algorithm is frequentist. And well, given the few times we've seen this, I trust you can actually make this happen on your own or check appropriate references. So once we do this, right? So once we solve for an updated zeta, we essentially check whether it's the same as the old zeta as a convergence parameter, or whether or not, for example, the likelihood actually improves. So that's for check for convergence, likelihood of parameter values. And if the convergence is not satisfied, then we essentially start again from step 2 and go back down again. Okay, so let's use that general formalization on the familiar first. So Gaussian mixture in Gaussian mixture models, how does that work? Right, so here's the complete data likelihood. Right, in here, Z and K is, as we covered last time, this is a binary assignment latent variable. This is different from the responsibility variable. And then because we're taking the log, the multiplying by prior and the Gaussian part are just separated, right? So complete data likelihood is pretty straightforward. And then this is the Q function, essentially. This is the Q of zeta old and zeta. And in particular, the expectation is taken over Z. The notation here emphasizes that the fact that expectation is taken over Z, but here Z is distributed according to the probability of the posterior, which is this guy, responsibility variable here. And then this part inside, we just looked at upstairs. We just put it down from here. Right. Okay. So let's take a mental break and then use this to revisit the connections between K-means and GMM again, and then we're going to look at Bernoulli mixtures. So here is a brief table that are extracted from the book on how the parameters are estimated for GMMs and K-means. So we saw most of this, but it's good to have this connection reinforced in a different different format. Most of it is sort of implied or explicitly written down in the first 2 slides of this lecture already. So the mu k are basically weighted sums, weighted or unweighted sums of the data points, right, in here. The covariance matrices are either weighted data covariances, or for k-means, they are essentially identity matrices that are also weighted the same across all the components. So the number of data points in each cluster is the sum of responsibility variables in the matrix we drew for each column, right? So they're like this. There's one interesting about pi k in that, right, so what are the cluster priors? In Gaussian mixture models, they are computed as the effective number of data points in the cluster over number of data points. In k-means, it actually does not matter what we use. Well, because of 2 reasons. And one of it is in the k-means algorithm, remember the calculation of pi k did not enter the picture, right? And then in, right, the other reason is in order to derive the equivalent, say, data likelihood and so on, it does not matter as long as each pi k is greater than 0. What this means is that, cluster cannot be empty. So if there is no data point assigned to that cluster, it will stay empty forever, because in the E step, we can't update its mu's. Right, well, if you force that, you'll get nans. Like in your programming, you'll get nans and so on. That's nasty. So in practice, right, so it really doesn't matter. We can treat them as uniform, or we can just, and the other advice is good to monitor this column sum of R and K to make sure that it's not 0, right? So this leads to, say, two kinds of practical questions. One is what we just mentioned. So can a cluster center die in each model, or what are the corner cases, and how do you handle it? With k-means, some packages will give you more options. So do you really insist on k cluster centers? If not, if a cluster dies, do you want to just shrink it to k-1 means? But if we believe k-means, the choice of k is correct, we could reinitialize that cluster, that cluster center by, say, let's say splitting the biggest cluster right now, or just randomly choose another data point to be its own center and then rerun k-means. So again, we'll talk about at the end about how to better choose random data points. Right, for Gaussian mixture models, it's a bit more complicated. So as you can see, this NK, for well-defined mu and sigmas, meaning when sigma is not singular, NK is never really 0. Right, so these are real values. The corner cases arise when, right, the estimate, basically this can be singular, right? So right, let me say they can be non-full rank. And this can become problems. So the intuition of a non-full rank covariance matrix in high dimensions, you can think about let's say in 3 dimensions, a full rank covariance matrix is sort of a ball or rugby ball rotated in space, right? But when it say it collapses into a rank 2 covariance matrix, then it becomes a ellipsoidal shaped pizza. And that is bad because when we evaluate this term here, like the Gaussian probabilities, the covariance matrix are being inverted, and we often work in the space of precision matrices, and that basically explodes. So dividing by 0 is not cool for the covariance matrix. So how do you deal with this in practice is that you can regularize sigma k to be full rank. Essentially add this quantity here exactly actually to the estimate of sigma k, or ensure that each of the single sigma k has the minimum. It should be positive semi-definite, and you can ensure that the minimum of its eigenvalues is at least epsilon. The book also has a discussion about the relative computational complexity of GMM and K-means, and also representational complexity. So obviously, as we talked about a few times here, so GMM is more flexible, right? In many senses, right? So it does a weighted sum, right? So it assigns soft responsibilities. In a lot of cases, we might think a cluster can be, a data point can be explained by more than one cluster, and that's a desirable property. And it also can have non-circular, non-ball-like, non-circular clusters, and that's nice, right? This is also more flexible. So flexibility comes at the cost. GMMs has essentially order of d squared parameters because of these. Let me write it slightly better. So order of d squared times k parameters, where k-means has order of d times k parameters, right? Because you only need to compute the mu's. So which one to choose? Because in practice, your GMMs are almost always initialized with k-means anyway, that can be a starting point for you to decide whether you want to move towards the more flexible GMM. If the k-means is good enough, then just stick with that. And k-means wouldn't have, well, obviously because of this term, it wouldn't have the collapsed non-full rank covariance matrix problem, right? In terms of the loss function being optimized, you can see that they look very different. In Gaussian mixture models, it's maximum likelihood. The complicated procedure we just talked about with respect to Q actually is maximum likelihood, as we will see. In K-means, it's square loss. But as we covered early on in this course, the inherent connection of these two will come out when we essentially take the log of the Gaussian probability. These two objective functions are actually kind of equivalent. And the thing you want to say is, okay, what about the log of pi's, right, which breaks up in itself? That's where the comment about the pi don't matter as long as it's greater than 0, right? So if we compute this likelihood and take epsilon tending to 0, we'll see that these two are like essentially the same kinds of objective functions. So that's enough, well, I guess, of Gaussian mixture models for this round. We'll come back. Now let's use the view of mixture models on some other mixture. So let us just another simplest mixture or probabilistic model that we have seen is Bernoulli distributions or coin tosses. So in here, what we're saying is we have D separate biased coins, right? Each with probability mu I of being coming up heads. And they are always tossed together. And we get observations X, D-dimensional observations X, where each of the small x is binary, and mu is a real vector. Probability of X, given this mu vector, is simply, we have used this exponentiation trick for binary variables many times. Basically, mu raised to the power X times 1 minus mu to the power of 1 minus x. Only one of these two terms is active, and then multiplied. They don't depend on each other, but they're always tossed together, so it's a multiply. So it's easy to see that the expectation of x is mu, and the covariance, they don't depend on each other, and the covariance of x is diagonal. Well, it's mu times 1 minus mu, same as individual Bernoullis. Now, if we examine a mixture of Bernoulli distributions, meaning that, okay, the x observation variables are still the same, right? X belongs to 0 and 1 in D dimensions. And now we assume there are essentially k different modes or components in the Bernoulli means, and then they have priors, similar to Gaussian mixtures. What is, right, so we can follow the machinery and write out the data likelihood as basically sum over the components weighted by the prior and the conditional probability of x given each component, and the conditional x of given each component is exactly the same as the one in the previous page, right? So from 9.44, we just change the subscript and get here. So by now you may ask, where are we talking about this? It's exactly the same. And yes, the expectation is also kind of exactly the same, except they are now weighted by the pi's. That's nice. So what's tricky is the covariance matrix, right? So when the covariance matrix of the D separate Bernoullis look like the individual Bernoullis, but now they don't. And the book has this throwaway comment saying, now the D different coins, seem to be coupled because of this model. And this is indeed the case, right? Where the sigma of k was the covariance matrix for each component. And now the covariance is a weighted sum of each component plus the outer product of the means, and then minus the expectation of the overall variable mean, and it's not a diagonal anymore in general. Why is this the case? So you can go ahead and derive this, right, from the definition of covariance matrices. It's not particularly informative, but the I guess pain point here is, where does the intuition of the coupling between different coins come from? You say, oh, I'm just tossing different coins. So what's happening here is that we have a z variable, which is hidden, and it takes value from 1 through k, right? And then we have an x variable. Let's say I'm just going to denote it as for each dimension, right? xd variable. But there is d copies of it. Okay, let me wipe this and draw something nicer. So that makes more sense. Basically, all of the d copies of the x variable depend on the same z. So this is the source of the interdependence of the d separate Bernoulli distributions. So if we only have one component, the d coins are sort of independent and they each have their mean. But then if we are forced to choose between k sets of means, meaning that within each set, right, if mu, say in component k, if mu1, how are we doing this? Right, so we're doing mu k1 and mu k2, right? So if mu k1 is high and mu k2 is low, that means if we're choosing component k, we're forcing a negative correlation between the first coin and the second coin. And that's the source of this correlation. Once you have this intuition, the rest of this section should be pretty straightforward. I'm not going to bore you with the mechanical things in this next page. I leave you to do this with the book. Basically, we can compute data likelihood, complete data likelihood, and also expectation of this complete data likelihood, or i.e. the Q term, theta old, theta term. And we, yes, the responsibility variables are all computed the same way. Notice that they are just, well, from the last page, we haven't spelled out the posterior, right? So basically, taking the conditional class component conditional probability and then just put one term upstairs and then normalize by the sum of the overall terms. And then this long-term inside is basically the complete data likelihood. Well, you get the idea. So at the end, the update rules are actually quite similar and simple. Right, so this is also a way of a high-level message to say that don't get scared of this latent variable formality. At the end, a lot of times you're rewarded with these simple update rules, basically, and they are possible to check with intuitions, right? So this is the posterior probability, and then the cluster size is the same with GMMs. The cluster means in here are weighted sum of the data points, which is the same, where each mu k here is a vector of d dimensions. Prior probability is the same, right? So in here, the authors actually quite ingeniously formalized the written MNIST digit data using the mixture of Bernoulli model, right? So we first convert the digits to binary, and then we make the cluster centers actually the different digits, right? If we fit a subset of MNIST data consisting of 2, 4, and 3, using 3 components, these are the cluster mean, or right, these are the cluster means. So note that despite the data is now binary, but the mu KIs are still real valued, and they look like the digits, which is good news. If we fit all of these data using 1 component rather than 3 components, for example, it will look like not quite like any of these digits. All right. Any questions so far? Nope. So let's move on. What we're going to talk about next is another view of the EM algorithm. And why does it really maximize the data likelihood, which is the quantity we want in the frequentist estimation task? Followed by 2 of the recent developments and a chit chat about SML 1. Okay. So in order to discuss this, we need to introduce a quantity that a lot of you may not have seen before. So this is called KL divergence, or Calhoun-Leuven divergence, because it's discovered independently by different people. This is covered in the end of chapter 1 as a prerequisite in the information series section. Right, you can use these equation numbers to find the corresponding content, but what it captures is basically a let me say it's a quote-unquote distance, a notion of how far away. Okay, let me wipe this. Okay, so how apart is distribution Px and Qx, right? Right. It's distance in quotes, or it's not really distance metric because, as you can see here, it's not symmetric. Here's how it's defined. Right. So it's basically the ratio between Qx and Px, taking the log, weighted by Px, right? Or expectation, in other words. So it's sort of the expectation of the negative log of Qx over Px over P over Px. So the information theory view, which we haven't covered in this class, we probably don't need to cover in detail if you're interested. But if you're interested, right, so this later term, if we can naturally break this down into 2 terms, the later term is what's called the information entropy of P of x, or how much uncertainty there is in P of x. If P of x is sort of very peaky, basically taking almost 1 value, there's no uncertainty, but if Px of x is very spread out, there's lots of uncertainty. So the first term, it's called cross entropy. So for those of you training neural networks, or we kind of talked about this. There's lots of, you've almost surely used cross entropy laws, and this is where it comes from, where the name comes from. It's cross because it's two different distributions. It's entropy because it looks like this. So the intuition of the KL divergence is if we have incorrectly represented Px with Q of x, meaning if we basically it's the difference of the cross entropy with the true entropy. How much more information do we need to recover P of x? Right. We can trivially verify that if P of x and Q of x are equal, then the log term is 0 everywhere, and the KL divergence is 0. So the claim we would want to make that is useful for this section is that the KL divergence is 0 if and only if P and Q are equal for all of x. It is otherwise greater than 0. Okay, how do we show this, right? Right, if you're into designing machine learning and models and proving their properties, Jensen's inequality is your friend. What this says is, okay, so if f of x is convex, so here's the intuition behind Jensen's inequality. We have seen convex functions, right? So say f of x is convex, right? If a function is convex, then basically the chord, the line connecting any 2 points sits above the function. What this means is a weighted, so basically, or informally speaking, so f of average x, which is here, and average of f of x, or weighted average of f of x. So if f is convex, then the expectation of f of x is greater or equal to the function value of the expectation, which is exactly what's expressed here in this 1.117, right? So if we just apply this Jensen's inequality, and notice that the log function is concave, and minus log, right? Log function is like this, right? And then minus log is convex. Then we plug it in, we get that KL divergence is greater or equal to 0. It's equal to 0 only when this function is flat, basically when P and Q are equal. Okay, so that's the preliminaries. So our goal is to show that the EM algorithm maximize the log likelihood function and get some intuition in the next 10 minutes or so. So notice that the data likelihood, this thing we see in a few times, basically the complete data likelihood marginalized by the latent variable z, we claim that it can be broken down into a likelihood of a Q function of z plus a KL divergence term between P and Q. And the two parts look like this. So now we just introduced a new function Q of Z. And the L term look rather like, right, the cross entropy between the complete likelihood and Q of Z. And then the KL is essentially the conditional, essentially the KL divergence between the posterior probability and Q of Z. Given what we said about the first view or first alternative view of EM today, this may look less strange than if you were encountering a code, right? So the main new thing here is this Q of Z quantity. It has not yet been defined, but all of these other terms we have seen already. And the derivation of 9.70 is here. I don't believe it's in the book. That's what. Yeah, it's not in the book. I'm enclosing the derivation here for your consumption at leisure. I don't particularly feel that we should go through this. Hopefully I've included enough notes for it to make sense. But the important part is we just need to introduce almost any distribution over Z, so that the sum over Z is 1. Notice that Q of Z, so the point is Q of Z is simpler in form, or it looks simpler than the posterior probability of Z given X and Z. So hopefully that helps. So let's just assume, well, trust me, and you can verify this derivation offline. If we take, we think, yeah, if we now believe the decomposition and in 9.70, our view of the breakdown can be graphically depicted as follows. So the log likelihood is a number. The log likelihood is not necessarily a positive number in practice, but let's just say, like in our head, we visualize it as, say, a line segment in some space. And this line segment is basically a sum of a KL divergence term, which is always positive, and then this L term, right? So we introduce nothing new. We just take this decomposition and draw it. So here is where EM comes in. Remember that in the EM algorithm, we always compute this responsibility or posterior variable probability of the hidden state given data. So we simply set Q of Z into this as this posterior probability. If we do so, then the KL divergence term, the second term in the previous decomposition, goes to 0, because simply the KL term is defined as follows. If we just write, as we said, KL is 0 if and only if the 2 Q of Z is equal to the numerator part. So now the picture becomes, the KL divergence shrinks to 0. The L term with respect to the theta odd, remember when we compute the E step, we're using theta odd, right? So the L term of theta odd equals the data likelihood. in the old model. Now remember what we said about M step with the curly Q function. So we just examine the definition of the L term here. If we plug in Q of Z as P of Z given X and theta old, what we get is essentially two terms in 9.71. So the first term, if we break down the log, right, is essentially this Q function that we looked at for quite a bit. And the second term, right, the second term, Q Z log, actually minus log Q of Z because it's in the denominator, is fixed when Q of Z is P of Z given X and theta old. Right, because yeah, remember when we're computing the post-E step, we assume the theta old is known, so this whole part is fixed. We're only trying to solve the theta in the numerator here. So maximize, in other words, if we solve for argmax curly Q with respect to this theta nu, we're essentially raising or maximizing this L term, right? Or the second part of the L term is fixed. So we're raising the L term by a little bit. And after that, the KL divergence term will not be zero anymore if theta nu and theta old are different. Then this is the updated picture, right? So when in the picture, in the page before, we have two quantities that are equal. In the next page, we're essentially making this L term bigger. And because we know there's this constraint of this log likelihood, data likelihood is this L term plus a positive number, right? KL is a positive number. We know that this part is getting bigger and the likelihood term is kind of getting bigger even more. So we can, so now the intuition for this L term is clear. So it is lower bound of the likelihood, right? Data likelihood. So this view of machine learning algorithms is very, very useful. We're not going to be able to cover in detail in this class. But if you make machine learning algorithms, right, so if you maximize the lower bound of the quantity that you really want, you are also maximizing the quantity you really want. And if the lower bound of the quantity is easier to maximize, you gain lots of computational advantages, and it can make intractable or exponentially complex algorithms actually trackable, which is this particular case. Yeah, variational algorithms in general are of this class, and there are many, basically many examples. If you read papers, you encounter some soon enough. So pictorially, right? So we already, the book already contains this nice picture of, yeah, pushing up the essentially pushing up the ceiling here. Maximizes the lower bound, actually push up the ceiling in this lower bound function, and it also pushes up the p function. Well, if we look at the likelihood function as a function of x, what happens, right? So, or actually as a function of, so the x is data set given, which is given. So the x-axis here is theta. So the red function denotes the likelihood function, which is rather wavy, and it's hard to find the global optimum one, as we covered in the neural net session. What the algorithm does is, say, if we find a lower bound function, L of Q and theta, which is a convex function, which have a unique maximum. For example, for Gaussian mixtures, and in fact, for any mixture components from the exponential family, including Bernoulli, multinomials, and so on, and log normals, and so on, they're convex. So there is a unique maximum that's easy to find in this lower bound function. And then now we find the lower bound and move. So this is theta old, and theta new is at the maximum of the lower bound. And we then now find the new lower bound function, which is again convex, but it's now the green function, right? So the lower bound function is higher, and then we can push it even higher. So we basically do this successively until we approach the maximum of the likelihood function in itself. Right, so the extension, what this also means is that we can have extended, well, generalized EM algorithms that we just need to improve some lower bounds rather than maximize it directly. So basically on this picture here, so as long as we pushes up the ceiling between the lower bound function and the likelihood, the likelihood will improve, right? The reason that doing this is sensible is that models such as K-means and Gaussian mixture models, we are not aiming to find the global optimum anyway. So because of weight symmetry, or basic parameter space symmetries, there's many maximums that are the same, and it's in general not possible to find the global optimum or even verify that you are at one, even if you know, like, if you find a minimum maximum, it's right. So, right. So there are names for this, right? Expectation conditional maximization seeks to maximize these for a subset of parameters. We can do incremental algorithms involving a subset of data points. So these may, yeah, if you have a complex EM procedure that's very slow, you could try these. So we covered the second, yet another view of EM, building on the first one, which shows that by doing EM, we are actually going towards a local maximum in the original data likelihood. Is there any questions? No? Then in the next 5 minutes, we're just going to quickly look at like what are the newer things in this very old topic of clustering, which is rather interesting. So a disclaimer is that I picked these two papers out of a large collection of papers. I would say K-means and Gaussian mixtures and their theoretical properties are was quite widely studied, or has been quite widely studied until the last time I looked, which was in the like late 2000s or 2010-ish. Here are just two papers that I read and liked. So the first one is by John Kleinberg, who is an author I'm familiar with, or if you have looked into the science of large networks, John Kleinberg has done many important results there. So he wrote this very neat paper on the impossibility theory of clustering. Basically, how do we define clusterings, right? So he starts by defining three desirable properties, but he shows that there is no property, right? No clustering algorithm that can satisfy all of them. The first one is scale invariance, right? So if we the theorem is there is no clustering function f that satisfies scale invariance, richness, and consistency, where f is a function that given a data set and a distance function and maps the data set into clusters. So ideally, we would want, if we just scale any distance function, we should have the same clustering result. The second one is richness. Basically, a clustering function is equal to the set of all partitions, meaning that it can represent all possible clusterings in set X. And then consistency is if there are two distance functions, and if f applied on one distance function results in a partition gamma, and then hopefully if D prime is a gamma transformation of D, then running f on the new distance function should have the same partition. So John Kleinberg basically in his paper have presented examples of clique clusters distance R and scale alpha, these are variances of what's called a single linkage hierarchical clustering algorithm. So we covered K-means and Gaussian mixture models, which are probabilistic version of clusterings. But there's a large class of clustering algorithms that basically looks at how close data points are, then split or merge clusters. If you have taken data mining or databases, you might have seen some of them. He's shown that common variants of those satisfy at most two of these properties. So for K-means, it's easy to verify that it does not satisfy the consistency property. Moreover, so what this also says is that K-means is so the scale across different dimensions matters. If the data is poorly scaled, if one data dimension is sort of between 0 and 1, but some other dimension is between -1,000 and 1,000, then the dimension with the large variation will dominate, which also means we should probably normalize our different data dimensions before doing K-means. The second work I wanted to highlight is K-means plus plus. It's a theoretically sound way of doing K-means or initializing K-means, which is also very fast. It's fast to initialize, and it also makes K-mean fast to converge. Now, the reason that I'm highlighting these two works is that both John Kleinberg and Sergei Vasilevsky are still actively doing research in machine learning and related areas. You'll probably come across papers from them. Feel free to have a look at their webpage, right? So this Kmeans ++ is proposed in this 2006 paper. The problem with K-means include, right? So what if a cluster center die, right? And the other problem is Sergey begins his paper by showing that randomly choosing data points can be arbitrarily bad, right? You may think, right, so instead of randomly choosing k data points as the starting centers, maybe I can spread the initial k points out somehow. And this is the intuition of his algorithm, right? So choose the first center uniformly at random among all data points, and then compute the distance of this data point to all the other data points that haven't chosen to be centers. And then we choose a data point or randomly pick a data point as a new center using a weighted probability distribution with a probability proportional to the distance, right, or square distance in essence. So we repeat steps 2 and 3 until all points have been chosen. So the thing about this algorithm is that it does spread out the points using like the intuition of points that are away from the nearest center that's already been chosen is more likely to be chosen. But it's also probabilistic in a way that, well, they have a higher probability to be chosen, but we don't greedily choose a point that's furthest away from all the existing centers, because that could just give us outliers, and yeah, outliers are bad, and as we know. So it's a probabilistic algorithm, and the original paper has guarantees of this. You can read about it. So that's all I wanted to say for today. We covered the EM algorithm in a fair bit of detail. You will get to practice the EM algorithm with graphical models in assignment 2. We also give you a glimpse about what people are actively working on in the past decade and a little bit. Is there any questions?
Hi, I have a question about the Kmeans ++. When we are selecting, randomly selecting the i's cluster center, does that mean we have to take into account the former I-1 cluster centers and compute a probability distribution?
Yes, let's elaborate this a little more. So Kmeans ++ is actually an n-squared algorithm, where n is the number of data points. So here is how it proceeds, right? So let's say, let me just draw data points randomly here. Okay, maybe there are 2 clusters, right? So let's do this. So let's say I first randomly select the data points, and let's say I wanted what k equals 3, right? I randomly select a data point as a cluster center. I get here, and then for the second point, I compute basically the distance to this. This is d square x. Right. Of this, every single point to this existing data center, right? And then I choose one data point that's sort of according to the probability of dx squared, right? Let's say I make that choice, right? Because it's sort of inversely, well, it's proportional to the distance. In principle, the furthest point, let's say here, this point will have the highest probability. Because I'm choosing probabilistically, I don't necessarily get to this highest, furthest point. Let's say, well, my algorithm, my random choice maybe gave me this point. Now things get a little bit more interesting, right? So in order to choose the third center, I essentially need to compute the distance between this any unchosen point to either of the two like centers, right? So for this point, I also compute these two distances, right? So the d square of x is, right, I wanted to maximize the distance between x. Right, I want the data, in order for the centers chosen to be spread out. So this is the d squared x for this particular point because it's closer to this one. So we're not using the distance to the other center as a probability there.
Oh, okay.
Right, essentially we do essentially k-means, but keeping the distance. Right, without updating the mean, but we do the step of k-means of assigning this to this cluster and then using the distance to the distances as probabilities.
Yeah. So we only choose finally only choose one distance.
Yes, we choose one of the distances.
Okay, great. Thank you.
Yep. Is there any other question? Okay, if not, we'll talk about assignment 1 for a little bit because we'll just run into my contact hour, and then at the end I will, when I post the video, I'll tag this section for the entire class. So the grades should all be on Gradescope right now. There are some people still with issues with the auto grader results not visible, but yeah, we'll look into that. The serial part is available too. So overall, the class did pretty well. So us, basically the lecturer and tutor team, we liked Gradescope for two main things. One is the like ease of use over Wattle for grading. And the second one, the most important one, is that it allows us to create and share explicit rubric items, right? You can in fact see all of the rubric items for each question for the entire class. You won't see the breakdown of how many people this rubric item has been used, but you can basically have a glance and look at what are the rest of the, what are the ways that like points can be deducted for each question. One reminder for the class is that people need to remember to link their submission pages to questions. Basically, okay, question 1.2 is on page 1, for example. So more like this is a multiple to multiple mapping. But if you don't tag it, it wastes tutors' time by a lot. So we would even say that for assignment 2, if people don't do this, there will be a small but non-trivial penalty. So that's a reminder. We'll remind people again when assignment 2 is released. So a few sort of themes that we have seen across different people. In the theory part, there is one question 4.2. When the derivation of that is incorrect, it often propagates to the rest of that question. So people tend to get basically all or not very much in question 4 because of this. So I encourage people who have, right, like not quite get question 4.2 to go over the solution, which will be soon released. I'll talk about the letter 2 first. So for programming question 2, it asks people to construct a neural network that classifies an XOR pattern. So we expect people to at least show workings of what, like how the weights leads to correct classification of the XOR pattern. You can say the weights are godsend. You somehow just obtain them, but you need to sort of verify that they work, rather than saying PyTorch gave me the weights and here they are. I just print them out. And then there are, I would say, a few and not too many people who had errors with an autograder in the programming part. And that resulted loss of mark. Essentially, if the autograder cannot run the test case, then yes, it will think you did not pass the test case naturally. So hopefully that, right, for people with computer science background, that hopefully that's not a surprise. For people without, just be more careful about auto-grading. And in assignment 2, we're going to sort of help people by giving more access to auto-graders, by including, or probably include a question in the outline with 0 marks where you can try auto-grader on some test cases, which is not the one that you're grading on, right? So finally, this PCA question, which there were also some discussion around the time of the quiz. So we've been talking about, and throughout literature, it's been sort of presented in mixed notations, right? So it concerns, so the intuition of PCA, if we draw it pictorially, right? We often drew like this. Let's say we have a rugby ball in 2D, or just an ellipsoid-shaped pizza in 2D. I often draw it like this. And then, like, I'll needly to say, this is the first principal component. That's very intuitive. This view, it seems to not assume that the data is centered, right? But in fact, what happens is that, remember that the covariance matrix of X, right, or random variable X as a vector is expectation of essentially X minus mu of X. Yeah, I should use a different bracket. Okay, never mind, I just use the same bracket, X minus mu of X. Right, so if we have this sort of uncentered picture and we remember to compute a covariance matrix by subtracting the mean, that's okay. But a lot of times, let's say somewhere, there's various places in a book, and you will see in the literature, and in because this expression is long, people tend to write, let's say, covariance matrix S equals, say, the matrix X times X transpose times X. So it's basically a matrix of these transposes of data vectors times itself. So in order to, right, so this is, in order for this to valid data is assumed to be centered. Right. So what basically the expression above does is that it first removes mu of x by essentially moving the coordinates here. So if we first perform centering on x by removing moving the coordinate there, then we do the rotation. So I prefer, this is the mental picture that people now operate on, right? So whenever we see PCA or principal components of covariance matrices and kernel matrices, as you will see in assignment 2 as well, your first reaction is whenever we see this expression, we assume X is centered. When X is not, we try to do something by basically first centering it and then do these matrix operations. In particular for kernel PCA, which you will do, basically marrying what we're going to talk about next week, kernels, to PCA, where we talk about in section 5, week 5. There is an intricacy about how you center a kernel if you can't compute X or phi of X. So that's covered in the book, right? So, but in your assignment, it's sort of more convenient to work directly in this view, right? Just going to make a note for, yeah. Right, when you encounter kernel PCA. So that's all. Is there any questions now? I'm going to stop the recording, and I'm going to stay online for a little more in case people have questions for me.